something you need to memorize, the properties of logs. I find it helpful to remember them as being parallel properties to the properties of exponents. You're familiar with the properties of exponents. If you're multiplying like bases, you can combine them by adding the exponents. With the properties of logs, if we're adding like bases, we can combine them using multiplication into a single logarithm. With exponents, if we're dividing like bases, we can combine them using subtraction. If we're subtracting logs, we can combine them using division into a single log. This one's a little harder to argue out. Just trust me on it. If you have an exponent, we can pull the exponent out in front and becomes a multiplication, a coefficient. And I think this one's fairly obvious. If you have two like bases, the exponents that are equal, then the exponents have to be equal. And if you have two like logs that are equal, then what's inside the logs have to be equal. IFS stands for if and only if. If this is true, this is true. If this is true, that's true. And if you're in the middle of a test and you can't quite remember how the log works, remember if you can verify some of these just playing around with your calculator. Try it. Take the natural log of 3 plus the natural log of 2. According to our properties, that should equal the natural log of 6. So compare that on your calculator. Same thing with the log of 8 to the power of 3. Compare that to 3 times the common log of 8. That can kind of reassure you when you're in the middle of a test and aren't sure if you've got the properties straight or not. Okay, this section, the homework problems are pretty boring, but basically it's just to give you practice using those properties of logarithms so you're comfortable with them before we start solving exponential and logarithmic equations coming up in the next couple sections. So using the property of logarithms, if they're multiplying if you have the log of the product, we can expand that and make it the log of the first plus the log of the second. And then using our other property, if we have an exponent, we can pull that out in front and get 3 times the log base 3 of y plus the log base 3 of x. So we're just expanding it out. Not by itself very interesting, but we'll use this in another section. Going the other direction, if we're starting with a logarithmic expression, we can maybe combine it using our properties into a single log. So this one here, since we have 5 times the log base 4 of x subtract 7, we can make that log base 4 of x subtract 7 to the power of 5. So we're pulling the coefficient up in front and becomes an exponent. And then if we have a log subtract a log, oh, I'm sorry, we did the same thing with the 3 here also. 3 and the coefficient of 3 became an exponent of 3. Then if we're subtracting the 2 logs, we can combine it into a single log using division. When asked whether or not we could think of the subtract 3 as being plus negative 3, we could. And then we'd have a log plus a log, but now our exponent's negative 3. And then if we're adding 2 logs, that would be a multiplication problem when we combine it. But with that negative exponent, this would then move down to the basement, and we'd have x subtract 7 to the 5 over x cubed, and the log of all that, base 4, the same result, whichever way you think about it. A couple more examples. Expanding this one, log base 2 of x squared times y to the 7th, all divided by z. Do one step at a time. It takes a little longer, but it's hard to go wrong. Because of the division, we can expand it with subtraction. And then we still have a multiplication problem in here. So this log we can expand into the sum of 2 logs. And then we've got some exponents. We can pull the exponents out in front to become coefficients. And we end up with 2 times the log base 2 of x plus 7 times the log base 2 of y, subtract the log base 2 of z. So that would be expanding it out. And then here's one where we're condensing, so we have this very long log expression. So again, just do one thing at a time. So first I took the coefficients, pulled them up so they become exponents. And then I worked from left to right. So with the subtraction, this would be the log base 2 of x cubed divided by y. And then we still have the plus log base 2 of z to the 4th to take care of. Because it's addition, this would be a multiplication problem when we combine the 2 logs into a single log. And then x cubed over y times z to the 4th, and you can put it over 1 if you like, would multiply together to give us x cubed z to the 4th all over y. And one more. Expanding the natural log of the square root of x times y. The multiplication would expand it to the sum of 2 logs. Now remember, the square root of x is the same thing as an exponent of x to the 1/2. So the square root of x, since we can write it as an exponent, we can then pull the exponent out in front and simplify it further. Okay, change your base formula. This is another thing you want to memorize. So how to trick our calculator into giving us logs with bases other than the common log base 10 and the natural log base e. So what we can do, just to give you the theory here, log base 4 of 25 will set it equal to y, and then we're going to rewrite it in exponential form. You should be real comfortable with that. Then what I'm going to do is take the natural log of both sides. So as long as we're doing the same thing to both sides of the equation, we can pretty much do what we want in algebra. Once we do that, a property of logs allows us to take this exponent of y, pull it out in front so it becomes a multiplication problem, and then we can divide both sides by the natural log of 4. That isolates the y, and it equals the natural log of 25 divided by the natural log of 4. So grab your calculator, type that in, be sure to put the parenthesis after the 25 before you do the division, and you should get about 2.32, goes on forever. And then just to double check yourself, come back up here and try 4 to the power of about 2.3219, and you should get approximately 25. So what we're finding when we're evaluating logs is the exponent that the base can be raised to that would equal the input of the log function. So just to lay that out formally, change your base formula. Log base b of x is the natural log of x divided by the natural log of b. You're going to want to memorize that for the test. You can actually use any other base besides the natural log. Common log is a good one also. It's convenient to use a base that's available on your calculator. So most calculators just have log base e and log base 10. And then to get your calculator to graph a base other than e or 10, what we do is if we want to graph log base 2 of x on your calculator, we type it in as y1 equals the natural log of x divided by the natural log of 2. So the natural log of the input divided by the natural log of whatever base we're interested in. When we do it by hand, we did this earlier, we get these points here in our function. On our calculator, I really zoomed in here to get this particular graph on the calculator. Here's 1, 2, 3, 4. And what your calculator does is a bad job. It has a real problem graphing anything with a vertical asymptote. And so looking at it, it looks like it hits the y-axis at -5 and just stops. It doesn't. It continues on down to negative infinity forever. So the range of a natural log function is negative infinity to positive infinity, and the domain is from 0 to infinity, not including the 0. You'll never actually reach the 0 for the x value, and the y values can go as negative as we want them to.